Good morning. Thank you to the organizers for this opportunity to speak. It's such a nice, just the whole thing is really nice, and I'm pleased to be here. I didn't get here until yesterday afternoon, so I missed most of the talks yesterday. And many of them sort of gave some preliminary stuff for my talk, so I'm not sure if I will have gotten that right. So some slack there. I'll probably overdo some stuff and leave some gaps in other places, but we'll see. All right, so just a quick outline, very big overview. So I'm going to just give some basic definitions, although I won't give all the definitions. We're covered already. And in particular, we'll target graph algebras to start, and then I'm going to talk about how functional analysis has inspired or gave intuition to results in ring theory, and then I'm going to talk the other way around, how ring theory results inspired or gave some intuition for results in functional analysis, in particular in the realm of groupoid algebras. And I will say this little disclaimer that the views and opinions expressed in this presentation are those of the speaker and do not necessarily reflect the views and positions of entities they represent. I just want to say this is my perspective and this is how my career has progressed, but I bet you if someone else gave this talk, an algebraist, for example, it might be quite different. Also, my daughter was watching me prepare my slides and she thought my talk seemed really boring. She asked if she could give a few little things to entertain. So there are 3 things she contributed, and one is this little fellow right here. So 3 of them. I think the implication is that I am a nerd. Anyway. And she was excited to hear how she was received. So I will have to report back. All right. She's 16. She's not like a baby. So groupoid. So I think you saw the definition of a groupoid in general. It is a generalization of a group where the operation is only partially defined, and as a result, there's not a unique identity element. A groupoid is a group with an identity crisis, and I just wanted to, so Paul Muley is known to say this regularly. I don't know if he still says it, but I feel like I wanted to give a shout out to Paul Muley because when I first learned about groupoids, it was actually his notes that sort of were my foundation. So yeah, that's a little guy with an identity crisis, I think. It's 2. All right, so I did write down the definition of a groupoid, but I think you've probably seen that yesterday. So we won't go through the details. Again, it's like a group, except the composition is only partially defined, or the multiplication. So then we define the set G2 to be the place where things are defined, and then it's associative where it makes sense, and their identities, etc. So I won't go through all the details of that. I think we're all using the same notation for sources and ranges. And so G is my groupoid, S and R are sources and ranges defined in this way, and then we use G0 for the unit space. So that's, I think, from yesterday. Again, I think this is mostly from yesterday, but not bad to recap. So we're going to be thinking in this talk mostly about étale groupoids. That's as general as I'll go. You can go more generally. I don't know if you did any more general yesterday. No. So we need our groupoids to come with a topology where the operations are continuous. And today, all my groupoids will be locally compact with Hausdorff unit space. So I think that's a difference from what you may have seen yesterday. I don't necessarily require the groupoid itself to be Hausdorff. So we will sort of try to talk about this in more general non-Hausdorff setting. And then an étale groupoid is a topological groupoid where the source map is a local homeomorphism onto an open subset of G. And that's equivalent to the range map being a local homeomorphism. Again, you've seen that already. I believe these came up yesterday as well, but they're going to be fundamental for what we're doing on open bisection. So if you have a local homeomorphism, each point in the groupoid has an open set around it where the source map will restrict to a homeomorphism, and that little open set is called an open bisection. So there's the definition. And one characterization of étale is it's étale. I think you might need locally compact with Hausdorff unit space, and then it's étale if and only if its basis has a basis of open bisections. So all groupoids. So just again, forgive me for reiterating things. So the tall groupoids are generalizations of discrete groups. So if your groupoid is actually a group, then it's a tall if and only if the group is discrete. And there's just some more examples. I did make it to Kevin's talk yesterday, and all his examples I believe are a tall. But discrete groups, so Becky's, Siak, and Renault groupoids, and even Kevin's groupoids arising from the action of a discrete group on a locally compact Hausdorff space. And I'll give you some more examples in a minute with symbol with that little diamond to flag that it's more examples. All right, so groupoid C-star algebras, it's here. Maybe I haven't provided enough details because I'm doing the non-Hausdorff setting, but I just don't think it matters that much what the precise details are, just to get the flavor. So we build the C-star algebra by first thinking about a vector space of functions. And when your groupoid's not Hausdorff, we need to be a little bit careful about what that vector space looks like. So we're going to talk about this curly C of G, which is in fact the span of functions f that are in C sub C of V for some open Hausdorff subset V of G. And that is a subvector space of the set of all functions from C to G, from G to C. That notation I never like, I have to look up, but I use it anyway. Meaning addition is pointwise and scalar multiplication is done pointwise. We also think of these functions, although they're defined as continuous functions with compact support on a little set V, we think of them as functions on all of G by defining them to be 0 outside of that V. So this is what you need to do when you're in a non-Hausdorff groupoid. If your groupoid is a Hausdorff, this is actually isomorphic to C sub C of all of G, but this is something different in the non-Hausdorff setting. And because of that way you're making them 0 outside of V, you get functions that aren't continuous, which is bothersome to some of us. I feel like myself, I grew up to Hausdorff groupoids, like I was trained that the non-Hausdorff aren't interesting, but the more I do, the more I'm interested in them. They are interesting. So anyway, all right, so once you have that vector space, then again, the construction, I don't know how much detail Aiden gave, but it's about the same as the Hausdorff one. So you need to, this can become a star algebra with respect to convolution and involution defined in that way. It's just the formula. So since we're étale, it just becomes a sum, and involution or the star defined here. And we'll skip the details, but you take the completion of that with respect to a particular norm, like the full norm or the reduced norm. It's not unique. There's exotic norms out there as well, which I think we'll be talking about this week. And that gives you the groupoid C-star algebra, a groupoid C-star algebra. And since today, I'm going to be talking about connections with ring theory. A lot of the subtleties between the full and reduced don't really come up in this setting, so I'm just going to use this notation. C-star G, even though that isn't a unique thing, we'll just be talking about groupoid C-star algebra. And if you want, we'll only think about groupoids where the reduced and full are the same, for example. Yep.
If G isn't Hausdorff, then there may not be a lot of such V's.
It's still étale, and the unit space is Hausdorff. So the basis of open bisections, each of those bisections will be one of those V's. I think I could have defined this differently and said V such that V is an open bisection, for example. So there will be lots of such V's in an étale groupoid with a Hausdorff unit space. All right, so forgive my funny handwriting, but I'm going to be forming a bigger picture here. But now we have a groupoid G, and we've talked about how to define a C-star algebra from it. And that's what I'm going to be talking about in functional analysis. And in this setting, my groupoid is étale. So we'll just leave that picture. All right, so in algebra, we're going to be talking about the Steinberg algebra of a groupoid. And that requires us to restrict what groupoids we look at. So we don't want just étale, we want what's called ample. I don't know if these came up yesterday. I don't think they did. They did? Okay, good. So an ample groupoid is an étale groupoid that's basis is not just open bisections, it has a basis of compact open bisections. So this is special in that compact open bisections And a Hausdorff groupoid are clopin sets. You have lots of clopin sets around. So it's spaces like and that kind of thing. But in fact, lots of the examples, so you see my diamond disappearing again. These are more examples of tall groupoids that are in fact ample. So again, discrete groups and discrete groupoids. Graph groupoids are ample. In general, diagonal Renault groupoids, they won't all be ample, but if the underlying space in which your local homeomorphism is on is totally disconnected and locally compact and Hausdorff, those will be ample. Again, not all group actions of discrete groups, but if you're acting on a space that's totally disconnected, those will be ample. I'm calling these XL Pardo groupoids. I don't know if that's officially a name of them, but the groupoids associated to actions of
Similar groups on similar graphs.
Yeah, those are all ample. Now, this is a little more vague, but in general, these groupoids you get associated to inverse semigroups are usually ample. So lots of the ones we care about, the people in this room care about, I would suggest are ample. I think I didn't say the higher rank graphs, but the higher rank graph ones are ample. It's written there. Okay. And then, so the Steinberg algebra is a construction from an ample groupoid. So in functional analysis, the C-star algebra is a complex algebra. Our scalars are coming from the complex numbers, but in ring theory side, we don't care so much about the complex numbers being the scalars. We just want it to be any commutative unital ring. I think I've seen some papers that remove the commutative part. I suspect you could remove the unital part, but I've never seen anybody try to do that. But anyway, so we have R being a commutative unital ring. Those are our coefficients of the algebra we're going to talk about. So it's built from characteristic functions. So characteristic function notation I'm going to use is just this 1 sub b notation. So that's I'm going to think of as a function from G to R that takes the value 1 if your gamma is in B and 0 otherwise. We might say, how would you do that if you weren't unital? See if you can think of a way, but I think you could. Anyway, so then so each one of those guys, if you have R being the complex numbers, then each one of these guys would actually be if you have an ample groupoid in one of those C sub C of V's. So this would be an element of that script C of G that we were talking about to construct the groupoid C-star algebra. So this is a subset of that. So the Steinberg algebra associated to this ample groupoid is just the span of the characteristic functions associated to compact open bisections. Kind of first written down in this way by Ben Steinberg. I'm disappointed he's not here, but in 2010. So again, it's a subset, a subvector, well, this time it's not a vector space, it's a module, a submodule of the functions from G to R. So the operations are pointwise addition and pointwise scalar multiplication. And in fact, the same convolution, and we don't have an involution anymore, the same convolution formula from before works here, but on generators of if B and D are each compact open bisections, you multiply these two characteristic functions, you get the product of the compact open bisections here, which it turns out is a compact open bisection. And this is sort of the connection of the inverse semigroup picture of what's going on here, in that this collection of compact open bisections is itself an inverse semigroup. So that is the Steinberg algebra. And when your coefficients are the complex numbers, this is a little bit not a precise enough statement, but the kind of norms we look at, the reduced norm or the full norm, the Steinberg algebra is dense inside of C of G, so that its completion. There is all of the C-star algebra for the reduced and the full norm. So there's that connection. All right, so that's the basic definition. So I had that picture before, and now I have this side. And here, I'm intentionally not always saying my groupoids are ample for the functional analysis side, but in the ring theory side, they have to be ample. And so we can start with the groupoid and go and build the Steinberg algebra. And what I'm going to be focusing on is sort of the techniques between, so you can make connections between the groupoid and the groupoid C-star algebra, trying to find properties that correspond with each other, or do the same thing, groupoid and Steinberg algebra. And what I'm going to be looking at is sort of the techniques you use to do that correspondence, how that might translate across to give you techniques in the algebra side or vice versa. And because of this picture, if you're in the ample setting, a lot of times you get if and only if kinds of statements between the groupoid C-star algebra and the Steinberg algebra, which often to me are surprising because the way the definitions work, but they almost never are direct. From here to here, they go through these techniques like you go through the groupoid. All right. So let's talk a little about graph algebra. So again, I think, and I wish I would have been there for Becky's talk to see what she said, so I don't like repeat, although anyway. So we'll have a directed graph. There's a picture of one, so I don't have to worry about conventions in that particular one. But we'll worry about conventions in a bit. So the idea is in both functional analysis and ring theory is to build a graph. I mean, in algebra for me, so that, you know, you build it from paths basically, so that multiplication is like concatenation of those edges or paths. And I put up the two kind of some good resources. So here is the C-star algebra book coming out of Ian Rayburn's CBMS conference on graph C-star algebras. That is really a lovely reference. Happy with the Southern Convention in particular. And this is actually in the early days of Leavitt path algebras. It's not actually a book, and it's maybe a proceedings more of a conference that happened at Malaga of the what's called Leavitt path algebras, which I don't think you've seen yet, but well, you probably have in your careers, but I mean in this conference. So we'll be talking about that. So let's start with the functional analysis side. Graph C-star algebras, again, you've seen this, but I think probably you saw, so there's two isomorphic approaches. There's the groupoid model, which you saw yesterday. Did you see the generators and relations model? So there's two ways you can do this. So one way is to build a groupoid as Becky described. The other way is to do a generators and relations thing, which we'll focus on that one actually in a minute. So I'll tell you what that's about. So you take a closed linear span of certain elements of B of H actually. And I think this was more for as much for my own entertainment as anything. So they sort of graph C-star algebras were introduced in the late 90s. And these are actually precisely the years I was a PhD student. The first paper that appeared was Kumjian, Pask, Rayburn, and Renault. As I've said many times in a conference, one of my favorite papers because it's graphs, groupoids, and Kunz-Krieger algebras. That graphs, groupoids thing really, thank you, David, was just made a magical connection for me because I'd heard lots of graph algebra talks and I was a groupoid girl and they always did generators and relations, and sort of sitting down with that paper really was like, oh, okay, now I understand because it did a groupoid. But I've decided to sort of look on MathSciNet for the first 5 years and just sort of pull off. This isn't every single paper, but I just searched graph C-star algebra anywhere and just pulled off a list of, just so you could see the kind of contributors. Some are missing some single author ones, but lots of Pask, Rayburn, Kumjian, etc. Jack Spielberg's here. Drennan and Tomford, again, this is when I was a PhD student with Mark Tomford, and Doug Drennan was a postdoc where I was, so I saw that one happening. There was something else I wanted to say. Anyway, so these are just sort of the introduction to graph C-star algebras, how this unfolded. Oh, I think I went this far because I wanted to get to this one, Patterson. I feel like this reference doesn't get enough credit. Patterson, and maybe people can correct me if I get this wrong, but I think he's the first one to write down the groupoid of a non-row finite graph. And so it took a while for that to happen, but I don't think he really gets credit for that as much as he deserves. And that's, want to flag that one. Is that right? Does anybody know? Like David, or I think that is. Okay.
Legitimately, I use that.
Not a technical term. So let me talk about these, the relations, generators and relations view. you didn't think I would be if you know me, you wouldn't necessarily think I would give this version of this talk, but I felt like this was probably, you hadn't seen this yet. And it was good in talking about how the functional analysis inspired the ring theory, at least one presentation. So here is a definition. So which convention have I chosen? The experts in the room, you'll have to decide. The relations look different depending on which convention you use, but I won't go through the details exactly, but I've listed this in this way with some redundancies. So a Kunz-Krieger E family in B of H is a collection of mutually orthogonal projections and partial isometries. So the projections are associated to the vertices, partial isometries associated to the edges that satisfy these 5 conditions. I'm sort of restricting right now to row finite graphs with no sources. No sources. The first 3 conditions are automatic by the assumptions of partial isometries and mutually orthogonal projections, but I just wanted to list them there because we'll see them again in a minute. And then the 4th and 5th, I think, are known as the Kunz-Krieger relations. And so the graph C-star algebra, you can think of as the closed span of a Kunz-Krieger E family, and it's in fact universal with respect to such a family, so that there is a universal Kunz-Krieger E family. Now, one of the presentations of a Leavitt path algebra, so this purely algebraic thing in ring theory, just kind of looks at this and algebraifies it. So I've written this in a particular way so that both the C-star algebra people think that doesn't quite look right, and the Leavitt path algebra people would be like, that doesn't quite look right, to try to make the pictures look compromise. But what is a Leavitt E family? So again, I'm going to think about now, not in B of H, just in some R algebra. We don't have projections and partial isometries. We just have PVs for each V and SEs. And now we have to be careful because we don't have a adjoint anymore, a star. So we just throw in some edges. So we have the edges E1, and then we make a new set of edges called E1 star, which is the same as E1, except we switch the direction of the arrows, which is confusing with that convention thing, but we have each edge, you have one going the forward direction or whatever direction you choose, and one going the other way with a star on it. And then you can define a Leavitt E family to be satisfying these 5 relations, and that's why I've signaled out these 1, 2, and 3 you get for free in functional analysis. They needed to make sure you got those, you don't get them free abstractly. And the other difference is, again, where the star appears. If there's typos, it could be one of them would be where my star is. So over here, the star is the adjoint, and over here, the star would be on the edge itself.
In the first condition in each of these, you have VPW is equal to the delta VW times V. Is that supposed to be?
Should be PV, sorry, typo, PV, thank you. Yeah, that's why Leavitt path algebra people don't actually use, that's the one spot maybe I've given a little Leavitt path algebra notation. I find it quite confusing, but they don't use the P's and the S's at all. They just call them V's and E's. But that doesn't present itself very well for this Leavitt E family. It doesn't let you talk about more than one family, so I prefer to do it this way. Yeah, so the Leavitt path algebra is the span of a Leavitt E family, and it's universal with respect to that. Again, you could construct a concrete one. Just using like a free algebra where you quotient out by the relations. And yeah, so this is called we'll use that notation LRE for the Leavitt path algebra. So just to name some contributors in this area. So first introduced around 2005, and I've put the first 2 papers where they're sort of credited as being introduced. So I've put Enrique's one, Ara Moreno and Pardo, in parentheses, because I'm thinking the way that Abrams around Pino did it is sort of functional analysis inspired the ring theory, but I think the way Enrique's team did it is more inspired by the ring theory itself. Like, so I put it in parentheses because I want to credit that they had done this, but it's a place where it's not necessarily functional analysis inspired. But I first met Gene Abrams actually at the CBMS conference that Ian Rayburn gave, that little book where he was trying to learn about graph algebras, and went on after that to have the be at the Malaga conference where they introduced these Leavitt path algebras. Really as generalizations of graph C-star algebras. So those were sort of the first two, and just to be fair, well, hold on. Who else contributed in these first 2 years? So Ian Rayburn himself did. You might not realize, I'm not sure he gets credit for it, but both he and Mark Tomford were contributors in this conference in Malaga. And Ian, I think his paper in there does row finite no sources and does uniqueness theorems for Levitt path algebras. So he was a contributor in the early days. So, and then I've listed a number of other people who've been involved. Again, I don't pretend this is an exhaustive list. I just tried to give you a feeling for the people who are involved. I think the people here, maybe it's just Enrique. And lots of these results, they're not all functional analysis inspiring ring theory, but lots of them are. You know, there's uniqueness theorems, there's simplicity results, there's pure infinite results in an algebraic setting, there's ultramatricial, which is like AF. There's Morita equivalence, there's K theory, at least the K0, K1 kind of stuff. So I would say lots of this is inspired by functional analysis. Although as it gets farther on, I think it's less and less. You know, like at first there were lots you can do, but then the algebraic questions sort of take over. And actually lots of the people I talk about right now about Levitt path algebra studying it, students don't have any idea about graph C-star algebras. So I need to spread the word maybe. Make sure you pay attention to the literature. Maybe that's the point of all my reference listing. Pay attention to the literature. Okay. So I'm suggesting, at least from my experience, that in the graph world, graph algebra world, most of the intuition has gone this way. Partly because I think graph algebra, C-star algebras were around first, but and not to trivialize, again, there's lots of interesting things to ask about in both areas that aren't quite relevant for the connection, but in general, I think it goes this way. Oh, I had to talk about it. So I had to talk about it because I'm trying to talk about connections and translating, and I think it actually breaks down like our ability to communicate with one another. So which direction do your arrows go? In the early papers, my favorite paper on graph groupoids and Kreuzer algebras, the chicken is walking backwards. So if you have edges E, F, and G, the convention for a path is to make the chicken walk backwards and have E, F, and G. But then in Ian's CBMS thing, and I think it's sort of inspired by work with Aidan and Trent Yeend on higher rank graphs and thinking about, well, which directions do the range and source projections of a partial isometry should match with the source and range in the graph. They switched. Ian made the switch in his CMMS notes to make the chicken walk forward, which is more natural.
There's only one. That was.
No, it's a chicken's footprint on there. Is the point? Sorry.
Oh, I see.
It's mine with a chicken footprint on
I
it.
see, okay.
I don't even think chickens can walk backwards, but now you might seem weird that I've called these both E, F, and G, but I did that on purpose because to go back and forth between the conventions, if you have one graph that you're using the forward walking chicken or the Southern convention, then if you want to translate that to get the same algebra out, you have to switch the arrows, the direction of the arrows in the graph, but it causes endless confusion. And it's not like, so I think in the Levitt path algebra, it's almost universal that it's all done this way. In the graph C-star algebra, Ian made the switch. Many other people made the switch, but not everybody made the switch. So, and it's hard teaching students like this idea about, well, they're the same, like they don't quite get like, oh, so what is the source of this path? I'm like, no, it's the one. This is the source still. So
I guess you're kind of leaving out the dynamics people too.
Yeah, what do you do?
It's just a finite type to the backwards walking, yeah.
Yeah, I mean, there's some reasons why, like, and I'm trying to be silly, like, obviously this is silly, chickens don't walk backwards.
I'm also on the top, so.
But I think it's more to motivate, like, because this is the more natural way, like, if you're just looking at paths, I know. There is it. In terms of, yes, paths in graph algebra, not graph algebra, in discrete mathematics graph theory, this is what a path is. So
Yes.
I'm not trying to. I'm just trying to maybe.
Doesn't it depend on what your native language is?
What's that?
Doesn't it depend on what your native language is? What if you're used to reading from right to left?
Yeah, maybe if you're.
But then aren't your functions in postfix?
The point is, I think it makes the translations difficult. It makes, especially going from Levitt path algebras to graph C-star algebras, that switch of the arrows makes it challenging. Like, what property are you trying to get from your graph? Even when I was early days, I remember trying to get a graph with a particular property. It wasn't like C-star algebra wasn't CCR or something. And I drew it and I showed it to somebody and they're like, well, which direction are your arrows going? I'm like, oh, that doesn't matter, does it? And it surely did. Anyway, okay. And I feel like Kevin did both conventions in his talk. I was trying to glean, and one time he had an arrow. He said, well, we don't let those. Sorry, not to pick on you. Okay, higher rank graphs. I'm not going to talk a lot about these, but I just want to say there's the same kind of progression happened here. So I'm not giving a formal definition, but it generalizes the path category of a directing graph to allow paths to have length n to the k. And again, in this setting, the reason I just talk about the conventions, that Southern convention is the right one. So it makes also the world of higher rank graph algebras, if you don't use that convention, it's a lot harder to try to think about higher rank graph as being a natural generalization. But in the higher rank graph C-star algebra setting, I'm not going to go 5 years, but sort of they were introduced in these papers. A couple of papers by Rayburn, Sims, and Yiend, Farthing, Muthi, and Yiend sort of did a generalization, but of course the original and huge impact paper by David and Alex. And then in the, so it's a similar progression. My LaTeX got messed up. Sorry, this should be up here labeling this. So these are Kumjian and Pask algebras, they're called, in recognition of the work of Kumjian and Pask in here. Although again, David or Alex have never actually worked in the area of Kumjian and Pask R algebras, I don't think. Excellent. Well, we're introduced in this paper. Oh, this isn't quite, I should have told my LaTeX is having a problem here. This is all up here. So in this paper by Aranda Pino Clark, that's not me, that's John Clark, who was at the University of Otago, Astrid on Hoof and Ian Rayburn, and it did the first introduction of higher rank graph, purely algebraic R algebras. And that was with no sources and row finite. And then Astrid I and a student, Claire Flynn get generalized to be locally convex or something. And I had a student, Josefat Pengalela, we generalized to locally. I mean, row finite, not row finite. What's my word? Yes, finitely aligned something. All right. But at first, this first one didn't have a groupoid, but by the time I was involved, actually, this one doesn't have a groupoid either, but this one does. All right, so I talked about the generators and relations of graph algebras, and in many of those first papers, Ian Rayburn would talk about removing the groupoid from things. So he would intentionally write papers where there wasn't a groupoid in there. We were at conflict. So in the graph C-star algebras were formulated with a groupoid model, but in the first, say, 5-7 years of Levitt path algebras, the groupoid was lost in translation. There wasn't a groupoid version of Levitt path algebras for quite a while. And so many of those, all those papers I pointed out about Levitt path algebras were just generators and relations papers. But we came along, we decided to get that groupoid back in there. So it's the same groupoid that Becky introduced you to yesterday. It's actually no groupoid associated to the boundary paths with respect to the shift map. And then we show, so Aidan and I with Cindy Farthing and Mark Tomford, and then Aidan and I get more general that the Levitt path algebra has a Steinberg algebra model with respect to that graph groupoid. Did the groupoid help? the Levitt path algebra. Again, I'm biased, but it's what it seemed to do from my experience is it helps when you're in non-row finite graphs. Like things, the relations get quite a bit messier and things get harder. So lots of those papers that I listed had the restriction to row finite, and having the groupoid model help kind of unplug what was happening to non-row finite. So it has helped, but let's get back on track of I want to talk about the insight between functional analysis and ring theory. So there's a question, when do two directed graphs E and F give rise to the same graph algebra? So this is where I think the groupoid model is fundamental to what is happening. So back to our functional analysis implies ring theory. So a paper that I also really love by Toka, Carlson, Nathan Brownlow, Michael Whitaker talks about when two graph C-star algebra are diagonally isomorphic. It's a special kind of isomorphism that preserves kind of the vertex projections. That happens if and only if the groupoids are the same. And what this result kind of does is, I think it's related to what Aidan was talking about yesterday, where if you have Cartan subalgebras, this Kumjian and Renault theory tells you how to, if you have an abstract C-star algebra with a Cartan subalgebra, no, let me take that back. If you have two groupoid C-star algebras and they're both Cartan and they're isomorphic, then the groupoids are isomorphic. And I think what Mike, Nathan and Toka do is generalize that where it doesn't have to be Cartan and this works for graphs. Maybe it's row finite graphs. I don't remember. I think it is row finite graphs. So Astrid and I, along with John Brown, were able to Levitt path algebra that one up. Again, looking very closely at what the C-star algebra one did. And then after that, there's a series of papers about this kind of thing, more general groupoid construction of getting, like, when is this two isomorphic algebra, groupoid algebras have isomorphic groupoids. So a series of papers by Carlson, Rout, Ara Bosrat, Hasrod, and Sims, Ben Steinberg, Carlson, Ruiz, Sims, and Tomford, and then Tristan and I have a very general sort of version. And actually, this is where I think there's some back and forth thing. Like this paper is a C-star paper. I don't know if it's true, but it seems like it gets some inspiration perhaps from some algebra knowledge happening from this paper. So yeah, some back and forth there. All right, one more place where functional analysis implies ring theory is in twists. That actually is not my daughter's contribution. I just stuck that in there myself. Because to me, that is a twist, although she said nobody knows that's called a twist.
I'll back you up, Lisa.
You call it a twist? Maybe it's my American.
Two versus the rest of the room.
So I'm educating you on all things like twists. All right, so as Aidan talked about some, I think, like this idea of twisted groupoid C-star algebras sort of appear, have a very important role in C-star algebra theory, especially results from Barlock and Lee, for example. It's intricately related to the classification program. And basically, I'm not giving definitions, but the theory tells us that C-star algebras that have diagonal or Cartan pairs are isomorphic to twisted groupoid C-star algebras. And so what I've done in a couple papers, so it's going to take a while to list off authors here, so maybe I won't, I'll just point to. So in this paper with Becky et al., we introduce a notion of discrete twists and twisted Steinberg algebras. And it actually wasn't like discrete twists are quite special, kind of like the ample thing. You need to restrict what you're looking at. They are special, and what kind of throws you is you think of the topology on the complex numbers as actually being discrete. That's why we call them discrete twists. So discrete twisted groupoids and twisted Steinberg algebras. And then this 9-author paper, which includes in the room would be Becky, me, and Aidan, and Ben if he were here. Well, and all of them if they were here. Oh, and Ying Ben. Sorry, Ying Ben. Who's here? Oh, and Jackie. Sorry. Sean Clark, Courtney, Lynn, McCormick, and Ramage. There's too many authors for me to keep track. Sorry. And then this one, in addition to those, has Gilles de Castro and Sims and Steinberg. I feel bad. where we do this diagonal and carton pair thing in the algebraic setting. One thing that so I will, if you've heard any of us give a talk about this and talk about how this kind of came to have so many authors, it was because we were working on it, this group. And Aiden and Gillis and Ben were also working on it separately, and we kind of proved similar things and found out we were both working on it and decided to join forces. But I will just give a shout out. So joining forces did require us to overcome an obstacle in that the Aiden team were looking at this inverse semi-group of normalizers. They were looking at the groupoid of germs associated to that. But we were, based on some experience we've had, like for example, work I did with Tristan, we're looking at ultrafilter groupoid. And so it was helpful to have this paper by, and I'm not going to do it again, Becky, me, Astrid Unhoof, Malcolm Jones, who's in the room, and Ying Fen, that said the two approaches to doing this groupoid were the same. I think that was really, Malcolm was the key contributor to that. Okay. So what about ring theory to functional analysis? Now, I grew up in analysis and would have thought there isn't going to be that much going in this direction. But the more I learn, the more I think I was kind of being arrogant, because I think there's a lot to be done going in this direction. Although I still feel like when I give talks, I encounter that sort of, oh, come on, it doesn't see the amenability stuff. It doesn't see any of that. It can't be. But so I'm going to start not chronologically, just continue on this twist thing. So one thing we've been able to do, so in this 9-author paper, not only do we have carton pairs and diagonal pairs, we have this generalization called a quasi-carton pair. So in a carton setting, you have that the subalgebra has to be a massa, a maximal abelian subalgebra, but we found in this purely algebraic setting, we could weaken that and have this slightly weaker thing that was definitely not carton. You know, like we have examples, like the group of integers is an example of a thing whose algebra, group algebra, which is its Steinberg algebra, is quasi-carton, but not carton. And show that when you're in this quasi-carton setting, you can still construct a groupoid and get an isomorphism working. And so Jackie et al. We started looking at this in the C-star setting, like what is that condition and what does it say? And we've realized that the condition in the C-star setting, if you impose that condition, actually implies carton, meaning this phenomenon of quasi-carton is actually a purely algebraic thing. So that is a paper we are just about ready to submit talking about that. Yep.
When you say, for instance, like the integers don't have doesn't have a carton but has a quasi-carton model, you're picking a particular subalgebra?
Yeah. So I'm talking, that is a good point. I mean, the integers as that groupoid.
Okay.
Because yeah,
Like,
well, that's exactly what demonstrates why this doesn't work, because the integers, the group C-star algebras of the integers is in fact the continuous functions on the circle, and that Fourier transform like helps us to see that this phenomenon, when you do the closure, you pick up things that make it so this doesn't work anymore. So that,
I mean, my point is more that the functions on the circle has a carton subalgebra. It's just a very trivial one of everything.
yeah, because
So
it's
this,
continuous itself.
yeah.
I mean,
So the,
so
this particular quasi-carton subalgebra quasi-carton pair, you pick just the copy of C corresponding to the unit in the integers, or is there a particular?
to show that it is quasi-carton, we mean the groupoid itself satisfies the property of being, but yeah, okay, so the algebra, maybe my flippant statement of the integers don't work. So there is an algebraic definition of quasi-carton that has nothing to do with the groupoid. We're saying if a groupoid, I mean, if you have an algebra that has a commutative subalgebra such that, and the condition is, there's a couple equivalent versions, like the conditional exploitation is implemented by idempotence, is how we phrase it. Or it satisfies, I think Ben coined the phrase, the local bisection hypothesis. which is that every normalizer is supported on a local bisection or an open bisection. So that is what it is. Then it's quasi-Cartan. And I'm trying to decide if the group algebra of the integers is quasi-Cartan, with the subalgebra being the identity, the complex numbers times the identity, whereas it's not Cartan with that particular subalgebra. So does that clarify? You're right, it is Cartan with itself being its subalgebra, but that's not, not what I meant. All right. Yeah, so I just was saying, in fact, what we were able to show in there using this insight we've got from the algebra techniques, that this version of a C-star algebraic local bisection hypothesis, which again gets sort of technical, but it talks about normalizers. Every normalizer is supported on a bisection. That's something you can talk about in the reduced C-star algebra of a groupoid if you think of them as functions, that in fact implies that G is an effective groupoid. So this is a converse to something Renault shows. Effective implies this thing. We were able to get the converse. All right, gotta go quick. So more ring theory implies functional analysis. I've talked about this one quite a bit, but right now for this little bit, let's talk about it's all Hausdorff algorithms. Again, I need to really be clear here that I'm thinking about the reduced and full being equal to each other. And then Renault says in his 1980, in his thesis, says that if your groupoid is minimal and topologically principal, then its C-star algebra is simple. And the question is the converse to that true? And so that was an open question for 30 years plus. And then, so John Brown, Cindy Farthing, Aidan, and I started thinking about this, whether the converse was true, and we actually got stuck pretty quickly. We hit a brick wall, but then we decided maybe this isn't how Aidan would tell this story, but we decided to turn to the question of simplicity of the Steinberg algebra and see if that was something we were able to do. We still were hitting that brick wall for a while because we're like, we can't quite get the topologically principal. We were trying to do a contrapositive kind of thing. And then we realized that topologically principal was in fact the wrong condition. And so we were able to show the ring theory result that the Steinberg algebra is algebraically simple, meaning just has no two-sided ideals, non-trivial, if and only if the groupoid is minimal and effective is the right condition. And it turns out there are settings, like we were sort of in a setting, where these two things are the same, but we needed the second countable for that to be true. And Hausdorff, and the proof that these two are the same requires a bare category theorem sort of thing. So it's outside of ZF. So that's what was getting us stuck. But once we got the right condition, then I think it flowed a little more naturally that we were able to prove the converse of Renault's result. So we were able to get that the groupoid C-star algebra is simple if and only if the groupoid is minimal and effective. And that really did use the intuition we gained from the algebraic setting. And then I was saying in my picture, sometimes you can get if and only ifs happening at the algebra level. So this is just stating that as a theorem, that if you're in an ample groupoid, that simplicity of the C-star algebra is the same as simplicity of the Steinberg algebra. And what's surprising about that to me is the definition of simple is different. Like a simple C-star algebra has no closed two-sided ideal, and this is just no ideals. So, and it went through the groupoid.
So this, if G is, you have this condition that only the C-star algebras are the same. So would you get a statement about the reduced C-star algebra if you?
Yeah, if you take that out, then one direction you get with a full and one direction you get with a reduced. And I don't remember, maybe Aidan can say which direction it is. In the proof, one of them definitely uses that we're using the universal norm, and one of them we concretely use the reduced norm.
Yeah, I stumbled over this in public once because the group is C-star simple. The group thought of as a groupoid would be sort of.
Yeah, I mean, it's still an interesting question whether group C-star algebra is the reduced one is simple, right? Like that's been a thing people are still thinking about. So we're sort of removing that and talking about the full one. Yep. But we were able to also, it's not the same result exactly, but use a similar technique for non-Hausdorff groupoid algebras and get a characterization. It's not exactly what I would like because you have to add a condition in non-Hausdorff that talks about functions, and it's not quite a groupoid condition, at least our version. But it still works, and this is with along with Rui Excel, Enrique Pardo, and Charles Starling. Okay, can I take a few more minutes? I think my time is up, sorry. Oh, it doesn't have to end at 50. Okay. So another place that I've had recent success in ring theory to functional analysis is in looking at this question. If you have a non-Hausdorff groupoid, are all the definitions of the full C-star algebra equivalent? And so what I mean by that is in the definition of the full C-star algebra, it talks about star homomorphisms, well, representations of this C of G, which are star homomorphisms, maybe just star homomorphisms, or maybe bounded with respect to the I norm, or bounded with respect to what Paul Muley and Dana Williams called the inductive limit topology, which isn't actually a topology in this setting necessarily that I can show. So the literature, they're different, like how it defines this. Kind of the nicest version is maybe Rui Excel's version, where he can show how to define the full C-star algebra with just the definition being representation is a star homomorphism. He shows that it's automatically bounded with respect to this. It's not a particular named thing, but, and then you can take the supremum over all of those to get the definition. So again, I'm sort of starting to get kind of technical, but I had a student, it's actually Aiden's PhD student, but he did an honors project with me. I had him start looking at, can you build the C-star algebra of an ample groupoid just by looking at the Steinberg algebra instead of that stinking curly C of G, because I find that thing is hard to work with. And he was successful in showing that. So you are able to just, talk about star homomorphisms from the Steinberg algebra to B of H and take the completion with respect to that, and build this. So that's nice. It's sort of a generalized approach where you don't have to worry about whether you're in C sub C of G or curly C. And as part of that, we were able to show that these star homomorphisms are always bounded with, again, we use this phrase with respect to the inductive limit topology, which is really uniform convergence on compact sets kind of thing. But this is what we were able to then take and get an et al. Version on this curly C. So we were using those techniques to get that those representations or star homomorphisms from curly C of G to B of H are always bounded with respect to the inductive limit topology. And then if you're allowing second countable, you have Renaud's disintegration theorem, kind of maybe proven in this generality by Paul and Dana, Muley and Williams, that says that then if you're bounded with respect to the inductive limitology, you're I norm bounded. And so for second countable groupoids, the full and C-star algebra, all these definitions we have are all defined. They give you the same result because you get this same kind of bounded. And I'll leave you with an open question. This definitely uses the second countability. I don't know the preciseness of where second countable comes up in the proof of the disintegration theorem, but I wonder if that can be different if your groupoid's not second countable. So I will stop there.